So in algebra, when you say that two groups are isomorphic to each other, algebraists consider those groups to be more or less the same. I mean, it would be better to say they behave equivalently, but we often just say they behave in the same way. And what we mean by that is they have the same structure. If one group has one property, then the other group has that same property. If you look at an element in one group and the way it behaves, its order, how it behaves in relation with the other elements, then the same thing is true for the corresponding element in the other group. And Theorem 6.2 and 6.3 summarize a lot of these important properties of isomorphisms, acting on elements and also acting on the groups. So let's just tick them off one by one. So if you have two groups that are isomorphic, G and G bar, then, and phi is our isomorphism from one to the other, then phi will take the identity in G to the identity in G bar. So the identity gets mapped to the identity. For every integer n and every group element, phi of a to the n is the same as phi of a, the whole thing, to the n. So taking powers of an element in G or in G bar doesn't matter. They carry across. Two elements in G commute if and only if their images in G bar also commute. So as a result, if one group is abelian, then the other group is also abelian, and that's an if and only if. 4, the order of the elements is the same. So if you have two corresponding elements, A and phi of A, then their orders have to be the same too. And number 5, if you have an integer k and some element b in G, and you're looking at the solutions of the equation a to the k equals b, that has the same number of solutions in G as the corresponding equation x to the k equals phi of b has in G bar. I keep saying prime, G bar. So those are important properties of isomorphisms acting on elements. And then Theorem 6.3 talks about the groups themselves. So if you have, again, two groups that are isomorphic with isomorphism phi, then one group is abelian if and only if the other group is abelian. One group is cyclic if and only if the other group is cyclic. And of course, if phi is an isomorphism from G to G bar, then phi inverse has to be an isomorphism from G bar to G. And then finally, if you have found a subgroup in G, so K is a subgroup of G, then when you're looking at the set phi of K, which has all the images of elements in our subgroup K, and you put all those together, then you get a subgroup of G bar. So phi takes subgroups to subgroups. Now, a consequence from all of this is that when you are looking at cyclic groups, there aren't that many of them. They aren't all that different. So if you have two cyclic groups and they have the same order, then they have to be isomorphic. So this is actually worth writing down, maybe even in red. Cyclic groups of the same order are isomorphic. And you could think about just, you have a cyclic group, it has a generator. Define an isomorphism from that generator to the generator in G bar, and then everything will behave exactly the same. So if you just look, if this is G, then this will be your G bar. Okay, in the next few videos we're going to do a few proofs for some of these elements, and some of them are also done